The universe runs on hidden code, and sometimes that code glitches. We are talking about real cosmic bugs, fractures in the fabric of space and time that make no sense under the rules we thought governed everything. These are not science fiction plots, they are documented anomalies, tiny whispers and massive roars from the cosmos that physicists from Einstein to Hawking have struggled to explain. Today, we are going on a tour of 25 of these profound mysteries. By the end, you will have a front row seat to the edges of human knowledge, places where our maps of reality simply stop. What happens when a spacecraft speeding into deep space suddenly slows down for no reason? Why does the echo of the Big Bang itself seem to point in a single, forbidden direction? We are about to dive into the glitches in the system. What do you think it means when the universe itself seems to break its own rules? Our first anomaly began with a whisper from a pair of brave mechanical explorers. The Pioneer 10 and Pioneer 11 spacecraft, after their historic missions to Jupiter and Saturn, were hurtling out of our solar system into the endless dark. Scientists tracked their every move with incredible precision, using the laws of gravity laid down by Newton and refined by Einstein to predict their exact paths. But something was off, something was ever so slightly wrong. As the decades passed, the tracking data revealed an impossible truth. Both spacecraft were slowing down. Not from hitting anything, not from solar wind, but as if an invisible, gentle hand was reaching out from the sun and pulling them back. This deceleration was tiny, less than a billionth of the gravity you feel standing on Earth, but it was there and it was constant. For over 30 years, this pioneer anomaly defied explanation. It was a phantom force, a whisper of a problem in our fundamental understanding of motion and gravity in deep space. The initial theories ranged from the mundane to the monumental. Could it be the gentle push of heat radiating from the spacecraft's own electronics and nuclear power source? That was the leading candidate, or were we seeing the first hints of something far stranger, like a flaw in Einstein's theory of gravity itself, or the influence of unseen dark matter? The scientific community largely settled on the thermal explanation. The idea was that heat from the spacecraft systems, radiating unevenly, acted like a tiny, unintended thruster pushing them backwards. But here is where the mystery deepens and why many still list this as an unresolved anomaly. The thermal models are incredibly complex, and some researchers argue the math does not quite add up. The predicted push from the heat does not perfectly match the observed pull on the spacecraft. It is close, tantalizingly close, but for a signal measured with such phenomenal accuracy over such vast distances, close is not always enough. The Pioneer anomaly stands as a monument to scientific humility. It reminds us that even our most trusted robotic ambassadors can send back messages we do not fully understand, messages written in the subtle language of velocity and time that hint at shadows in the laws of physics. Yet the whispers from deep space were just the beginning. Closer to home, another anomaly was playing out in plain sight, one that seemed to defy the very precision of celestial mechanics. It is called the flyby anomaly. When our robotic explorers need a speed boost to reach the outer planets, engineers use a brilliant trick, a gravitational slingshot. They aim a spacecraft to skim past a planet, using its immense gravity like a cosmic whip to fling the probe onward, gaining velocity with perfect, predictable efficiency. At least that is how it is supposed to work, but during several key Earth flybys, the math broke down. Spacecraft like Galileo on its way to Jupiter, and later the comet chaser Rosetta, received an unexpected and unexplained extra kick. As they whipped around our planet, their velocity increased just a tiny bit more than every single calculation predicted. This was not a gradual drift like the Pioneer effect. This was a sudden, specific anomaly tied to the moment of closest approach, a mysterious bonus in speed that appeared and then vanished. The discrepancy was minute, a change measured in mere millimeters per second, but in the hyper-precise world of orbital dynamics, that is a glaring red flag. It suggested something fundamental was missing from our models. Was Earth's gravity not quite as uniform as we thought? Could the planet's rotation be interacting with the spacecraft in some unknown way, like a spinning top imparting a faint, extra twist? Some researchers even looked at the data and saw a pattern, a hint that the anomaly might be connected to the difference between the spacecraft's incoming and outgoing trajectories relative to Earth's equator. It was as if our planet had a subtle, directional stickiness we had never accounted for. The quest to solve this puzzle continues. Modern missions with even better tracking technology are scrutinized for the same effect. Each new flyby is a test, a chance to see if this phantom boost is real, repeatable, and ultimately decipherable. It is a reminder that even our own home planet, mapped and measured in exquisite detail, might still hold secrets in its gravitational embrace, secrets that only a passing spacecraft traveling at impossible speeds can reveal. But these gravitational whispers from within our solar system are just local curiosities compared to a discovery that threatens the very foundation of modern cosmology, a discovery etched into the oldest light in the universe. To understand it, we must look back nearly 14 billion years to the moment the cosmos became transparent. After the Big Bang's unimaginable fireball cooled, the universe filled with a bath of radiation, a primal glow. That glow, stretched and faded by eons of expansion, still reaches us today as the cosmic microwave background. It is the universe's baby picture, a snapshot of its infancy, and for decades, scientists believed it showed a perfectly smooth and uniform newborn cosmos, just as the Standard Model predicted. This assumption is enshrined as the cosmological principle, the idea that on the largest scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction, with no special place and no preferred axis. Then, in the early 2000s, satellites designed to map this ancient light with unprecedented precision delivered a shock. Buried in the subtle temperature variations of that microwave static, the hot and cold spots that seeded all future galaxies, was a pattern that should not exist. The data revealed a strange alignment, a preferred direction in space that the hotspots seemed to subtly favor. Researchers half-jokingly dubbed it the axis of evil because, if real, it undermines the beautiful, simple assumption of a uniform universe. Think of it like this: you are looking at a vast, supposedly random field of dandelions. Statistically, they should point in every direction equally. But if you study them closely, you find a faint but undeniable tendency for them all to lean slightly toward the east. That is the essence of the axis of evil. It suggests the universe might have a large-scale structure, a cosmic grain like wood, that gives it a fundamental orientation. The implications are staggering. It could mean our place in the cosmos is special after all, that we are aligned with some grand, universal architecture. Or, perhaps more disturbingly, it could indicate that the entire observable universe is just a tiny part of a far vaster and more bizarre structure, and we are seeing the imprint of that greater reality. For over 20 years, cosmologists have wrestled with this signal. Is it a genuine feature of the cosmos or a monumental statistical fluke, a trick of the data? Could it be contamination from our own galaxy's foreground light? Every new analysis and more sensitive map has been scrutinized, and the anomaly stubbornly persists, a faint scar on the face of creation that refuses to be explained away. It remains one of the most profound puzzles in all of science, a whisper from the dawn of time that seems to say the universe is not as random, not as isotropic, and not as simple as we ever dared to believe. If the cosmic microwave background hints at a hidden axis, then its most violent offspring, the great clusters of galaxies, are caught in a full-blown stampede. Across hundreds of millions of light-years, these immense structures, each containing thousands of galaxies, are not just drifting apart with the universe's expansion. They are racing. Observations from the Wilkinson Microwave Anisotropy Probe and later missions tracked the motion of these colossal clusters by studying a subtle distortion in the cosmic microwave background, a kind of shadow they cast as they plow through space. The data revealed something that should be impossible. These clusters are streaming at incredible speeds, over 2 million miles per hour, and they are all moving in the same direction. Scientists call this phenomenon dark flow. It is as if every continent on Earth suddenly started sliding relentlessly toward a single point in the Pacific Ocean. The force required to move such unfathomable mass is beyond anything we can see or measure in our observable universe. This is not the gentle tug of a nearby supercluster. This is a pull of terrifying magnitude coming from somewhere out there beyond the cosmic horizon. The most mind-bending explanation is that dark flow is the gravitational fingerprint of something entirely outside our cosmic bubble. Our entire observable universe, nearly 100 billion light-years across, might be just one island in an infinite multiverse sea. The colossal pull could be coming from another universe, a neighboring bubble of reality brushing up against our own, its immense mass warping the fabric of space-time on a scale we can barely comprehend. Alternatively, it might be evidence of a structure that predates our own Big Bang, a relic from a previous cosmic cycle whose gravitational echo still tugs at everything we see. The concept is so radical that it remains fiercely debated. Skeptics argue it could be a systematic error in the incredibly complex data analysis. Yet, as with the axis of evil, the signal persists in newer observations, a river of galaxies flowing toward a source we cannot see, toward a destination that may not even exist within our reality. It forces us to ask a haunting question. What could possibly be so massive, so powerful, that it commands the motion of the universe's largest structures from beyond the edge of everything we know? But that immense pull from beyond the cosmic horizon is not the only strange current in our universe. Closer to home, our own galactic neighborhood is caught in a powerful, mysterious river. For decades, astronomers have known our Milky Way galaxy is not drifting aimlessly through the void. Along with our local group of galaxies, we are all rushing at a staggering speed of over 1 million miles per hour toward a specific point in the constellation Centaurus. The source of this incredible motion is a gravitational monster, a region of space so dense it is dragging hundreds of thousands of galaxies toward it. We call this phenomenon the Great Attractor. The problem is we cannot see it. From our vantage point on Earth, the core of this gravitational anomaly lies directly behind the thickest, most crowded plane of our own Milky Way galaxy. This area is known as the Zone of Avoidance, a dusty, star-swamped band that blocks our optical view of the universe beyond, like trying to see a distant city through a dense, glowing fog. For years, the Great Attractor was just a ghost, inferred only by the motion of everything around us. How do you map something you cannot see? You change your eyes. Astronomers turn to telescopes that see in wavelengths of light that can pierce through the galactic dust, like infrared and X-ray observatories. Peering through the cosmic fog, they began to unveil the hidden landscape. What they found was astonishing. The heart of the pull appears to be centered on a massive cluster of galaxies called the Norma cluster, located about 220 million light-years away. This cluster is immensely heavy, but here is the twist. Its gravity alone is not nearly strong enough to account for the tremendous velocity we observe. The search continued, revealing an even larger structure behind it, the Shapley supercluster, one of the most massive concentrations of matter in the observable universe. Yet, even combining the pull of Norma and the colossal Shapley supercluster, the math still falls short. The full force of the Great Attractor remains unexplained. It suggests there is even more mass hidden in that direction, mass we have yet to fully map, perhaps in the form of vast filaments of dark matter weaving the cosmos together. So we are left with a profound realization. Our entire galaxy, with its hundreds of billions of stars, is being hauled on a cosmic conveyor belt toward a shadowy, unseen source of gravity. We know the general direction, we have identified some of the major landmarks, but the true engine of this great motion, the ultimate anchor of this river of galaxies, remains a ghost in the machine, a reminder that the most powerful forces in the universe can still hide in plain sight, or rather in plain darkness. This relentless pull toward the Great Attractor is a mystery of immense scale, but our own solar system holds a boundary just as puzzling, a place where the expected cosmic traffic simply vanishes. Far beyond the orbit of Neptune, in the cold, dark realm of the Kuiper belt, astronomers have mapped thousands of icy remnants from the solar system's birth. These frozen worlds, including Pluto, are the leftover building blocks of planets, and for years models predicted their population would continue growing denser for billions of miles into the deep freeze. But the data tells a different story. At a distance of about 50 astronomical units from the Sun, roughly where Pluto orbits, the number of detected objects is strong. Yet, just a little farther out, around 50 astronomical units, the population doesn't just thin out, it plummets. This is the Kuiper Cliff, a dramatic and unexpected edge to the debris field of our solar system. It is as if you were walking through a forest that gets progressively thicker, only to suddenly step off a sheer edge into an empty plain. The drop-off is so sharp and so clean that it cannot be explained by observational bias alone. Our telescopes are perfectly capable of seeing objects beyond this point, but they simply are not there in the numbers our formation models demand. So, what carved this cliff into the architecture of our cosmic neighborhood? One compelling theory points to the gravitational hand of a hidden architect. The abrupt edge could be the signature of an unseen, massive planet, a true Planet 9, orbiting far beyond the Kuiper belt. The gravity of such a world could have shepherded the icy bodies inward, clearing out a vast zone beyond its own orbit and sculpting that sharp boundary we see today. It is a cosmic vacuum cleaner whose presence we infer only from the empty space it left behind. Another possibility is more fundamental, reaching back to the solar system's infancy. Perhaps the primordial disk of gas and dust from which all the planets formed simply had a natural, sharp edge at that distance. Maybe the material from which these icy bodies could coalesce ran out, like a construction site that exhausted its supplies. This would mean our solar system's building plan had a predefined limit written into it from the very beginning, yet both explanations have their problems. A Planet 9 of the required size and orbit has proven frustratingly elusive to directly detect, and a primordial disk with such a clean cutoff challenges our understanding of how these cosmic nurseries behave. The Kuiper Cliff, therefore, stands as a silent fence at the edge of our known planetary system. It is a boundary that tells us our inventory of the solar system is incomplete, that either a hidden world waits in the darkness or our story of how everything here assembled is missing a crucial chapter. Every new survey that scans that distant darkness is not just looking for new objects, it is reading the final sentence of our solar system's construction manual, a sentence we have not yet fully deciphered. While the Kuiper Cliff marks a boundary in our physical backyard, another type of frontier was being probed from an Ohio field in the summer of 1977, listening for whispers not of gravity but of intelligence. On August 15th, a narrowband radio signal, blazing at a frequency that hydrogen atoms naturally emit in the quiet of space, pierced the Big Ear telescope's receiver. It was not a random burst of static. It rose in intensity for exactly 72 seconds, matching precisely the time it would take for a fixed point in the sky to drift through the telescope's stationary beam, and then it vanished. The signal was so powerful, so perfectly aligned with an expected hallmark of an artificial beacon, that when volunteer astronomer Jerry Amon reviewed the computer printout the next day, he circled the alphanumeric sequence representing its incredible strength and simply wrote, "Wow." In the margin, that single word named one of the most tantalizing and enduring mysteries in the search for extraterrestrial intelligence. The WOW signal's profile was textbook for what scientists imagined a deliberate transmission from the stars might look like. It was narrowly focused on one specific frequency, a feat nature almost never accomplishes without help. Its intensity curve was a perfect match for a celestial source. And it came from a region in the constellation Sagittarius devoid of any obvious natural cosmic radio sources. For that brief moment, it seemed the universe had finally said hello. The immediate and obvious next step was to listen again. Astronomers pointed every available instrument toward that same patch of sky, again and again for decades. They listened for a repeat, for a pattern, for any further hint. The silence that followed was absolute. The signal never returned. In the absence of a repeatable observation, theories blossomed. Could it have been a reflection of a human-made satellite off a piece of space debris? The frequency used was supposedly protected, reserved for scientific use, but a rogue transmission was possible. Perhaps it was an unknown natural astrophysical event, a transient flare of a type we have never seen before or since. Years later, a controversial suggestion emerged that it might have been generated by hydrogen clouds surrounding a passing comet, but that explanation was swiftly dismantled, as the specific comets proposed were not in that part of the sky at that time. The enduring power of the WOW signal lies in its perfect, frustrating ambiguity. It was a one-time event that fit the predicted signature of an artificial beacon with uncanny precision, yet it remains forever unverified. It stands as a cosmic sigh, a brief, brilliant flicker on the radio dial that ignited our imagination and then retreated into the noise of the universe, leaving behind a single, haunting question written on a faded printout. What or who for 72 seconds in 1977 was calling out from the dark? While the WOW signal was a fleeting whisper, the center of our own galaxy broadcasts a continuous, deafening roar in a language of pure energy. For over a decade, the Fermi Gamma Ray Space Telescope has been mapping the sky in gamma rays, the most powerful form of light in the universe, born from the most violent events imaginable. Its view of the Milky Way's heart should be a familiar one, a predictable glow from known sources like spinning neutron stars and the remnants of ancient supernova. But superimposed on that expected map is something bizarre, a colossal and unexplained excess of gamma-ray radiation that blooms from the galactic core. This is the galactic center excess, a fog of high-energy light with no clear origin. The shape of this excess is particularly telling. It is smooth, symmetrical, and spreads out from the center in a sphere, precisely the profile you would expect if it were produced by something that permeates the entire galactic bulge, something invisible that fills the space between the stars. That description points directly to one of the universe's greatest mysteries, dark matter. The leading and most thrilling hypothesis is that we are seeing dark matter particles annihilating each other. According to this idea, when two of these hypothetical particles collide in the dense environment of the galactic center, they would obliterate each other in a flash of energy, producing the gamma rays that Fermi detects. It would be the first indirect glimpse of dark matter's true nature, a monumental discovery. But there is a compelling alternative, one that resides in the realm of the known but unseen. The glow could come from a vast population of millisecond pulsars, the ultra-dense, rapidly spinning corpses of dead stars. These cosmic lighthouses beam out intense radiation, including gamma rays, and thousands of them clustered in the galactic center could collectively produce that smooth, excess glow. The problem is, our current telescopes cannot resolve individual point sources in that incredibly crowded and distant region to confirm their presence. So we are left with a cosmic detective story with two prime suspects, and the fate of modern physics hangs in the balance. Is the signal a fingerprint of the universe's missing mass, or is it simply a previously uncounted choir of stellar corpses? Distinguishing between these possibilities is one of the most urgent quests in astrophysics. New telescopes and more sophisticated analyzers are scrutinizing the signal's finest details, looking for any tiny lumpiness that would betray the presence of pulsars or any feature that perfectly matches a specific dark matter model. The answer, hidden in that relentless gamma-ray fog, could either unveil a fundamental component of reality or reveal a new chapter in stellar evolution, proving once again that the universe's loudest signals are often its most difficult to interpret. The gamma-ray roar from the galactic center is a puzzle of what exists now, but to find an anomaly written into the very atoms of creation, we must look back to the first minutes of everything. In the searing heat of the newborn universe, just 3 to 20 minutes after the Big Bang, the entire cosmos was a nuclear fusion reactor. This brief, violent period, called Big Bang nucleosynthesis, forged the first atomic nuclei from a soup of protons and neutrons. The math governing this process is exquisitely precise. By knowing the universe's density and expansion rate at that time, physicists can calculate exactly how much of each light element should have been cooked up. For 2 of the 3 primary products, the predictions match reality with stunning accuracy. The observed abundance of helium-4 in the oldest stars and gas clouds fits the theory perfectly. Deuterium, a heavy form of hydrogen, also aligns beautifully with the cosmic recipe, but for the third element, lithium-7, the cosmic books do not balance. The universe should have left the forge with about 3 times more lithium-7 than we actually find when we look at the atmospheres of the most ancient stars in our galaxy. These stellar relics are time capsules, their chemical composition largely unchanged since they formed from the primordial gas. They consistently show only a third of the predicted lithium. This is not a small accounting error. It is a fundamental mismatch between our theory of the universe's birth and the forensic evidence left behind. So where did the lithium go? One possibility is that our understanding of stars is flawed. Perhaps these ancient stars have internal processes that slowly destroy lithium over their multi-billion-year lives, dredging it down from their atmospheres into their hot interiors where it is fused into heavier elements. Astronomers have searched for this mechanism, but so far, no model convincingly explains the uniform depletion seen across so many different stars. The other, more radical possibility is that our picture of the first 3 minutes is incomplete. Maybe an unknown form of exotic particle, like a certain type of dark matter, was present during nucleosynthesis and altered the nuclear reaction rates, suppressing lithium production. Or perhaps the constants of nature, like the strength of the nuclear force, were subtly different in that extreme environment. The lithium problem is a quiet but profound anomaly. It tells us that while we have the broad strokes of cosmic history correct, a specific line in the opening paragraph is wrong. Either the oldest stars in the cosmos are hiding something from us, or the universe's first nuclear fire burned by a set of rules we have not yet fully deciphered. Lithium's missing atoms are a puzzle of cosmic accounting, but sometimes the anomalies we find are not about what is missing, but about something that should not exist at all. Deep within the nucleus of every atom, the rules are written by the strong nuclear force, the glue that binds protons and neutrons together. This force has a strict and well-understood rulebook. It allows pairs of neutrons to exist briefly, and the famous neutronium inside neutron stars is held together by gravity, not pure nuclear bonds, but a stable cluster of neutrons alone with no protons to mediate the bond is expressly forbidden. Or so we thought. In 2002, a team at the Grand Accélérateur National d'Ions Lourdes in France was smashing a beryllium target with a beam of lithium nuclei. They were looking for something else entirely when their detectors picked up a signal that made no sense. The data suggested the fleeting creation of a particle composed of 4 neutrons and nothing else. They called it the tetraneutron. For a fraction of a nanosecond, it seemed the impossible had happened. This was not just a new particle, it was a rebellion against the established laws of nuclear physics. The strong force, as we understand it, simply cannot bind four neutrons into a resonant state. It would be like trying to build a stable arch using only identical magnets all repelling each other. The structure should instantly fly apart. The initial finding was met with intense skepticism. Perhaps the signal was a misinterpretation, a statistical fluke, or the result of an unexpected background reaction. For over a decade, the tetraneutron remained a ghost in the data, an unconfirmed anomaly that many physicists dismissed as an error. Then, in 2016, a different team in Japan attempted to recreate the conditions. They used a different method, firing a beam of helium-8 nuclei at a helium-4 target. Their sophisticated detectors again captured a signature consistent with a 4-neutron resonance. The ghost had returned, stronger this time. The implications of a confirmed tetraneutron are staggering. It would force a fundamental rewrite of our understanding of the strong force. The models that have successfully described nuclear interactions for decades would have to be amended to allow for this new, exotic form of matter. It could open the door to other multineutron states, suggesting an entirely new nuclear landscape we never knew was there. Some theorists have proposed that if the tetraneutron is real, it might only exist as an extremely short-lived resonance, a temporary, vibrating structure that forms just before it disintegrates, a kind of nuclear mirage that pushes the laws of physics to their absolute limit. The hunt is now on for definitive proof. Laboratories around the world are designing ever more precise experiments to either pin down the tetraneutron's properties with certainty or finally lay the idea to rest. This is not just a search for a new particle, it is a stress test for the very framework of nuclear physics. The question is simple yet profound. Did we witness a brief, impossible gathering of four solitary neutrons, or was it merely a cosmic illusion? The answer will tell us if one of nature's most fundamental forces has been hiding a secret chapter all along. The tetraneutron challenges the rules binding the atomic nucleus, but another anomaly seemed to break a law considered unbreakable, the conservation of momentum. For over a decade, a strange device no larger than a household appliance sparked a firestorm in physics and engineering. It was called the M-drive, short for electromagnetic drive, and its claim was audacious. It promised thrust, a gentle push through space without expelling any propellant whatsoever. In a universe where every action must have an equal and opposite reaction, this was like trying to move a car forward by sitting inside and pushing on the dashboard. The design was deceptively simple, a sealed, truncated copper cone. When microwaves were bounced around inside this cavity, their resonant energy was supposed to create a subtle pressure difference between the wider and narrower ends, generating a net thrust toward the wider side. No fuel tanks, no exhaust plume, just electricity converted directly into motion. The idea originated not from a major space agency, but from a British inventor named Roger Scheuer in the early 2000s. For years, it lingered on the fringes, dismissed as wishful thinking that violated Newton's third law. Then, in 2016, a team at NASA Eagleworks Laboratory, a group dedicated to investigating advanced propulsion concepts, published a peer-reviewed paper. They reported testing an M-drive in a hard vacuum and measured a tiny but persistent thrust, a force so small it was measured in micronewtons, but a force nonetheless. This was the spark that ignited the controversy. If the effect was real, it would revolutionize space travel. Satellites could maneuver indefinitely without fuel. Probes could reach the outer planets in months instead of years, and interstellar travel would shift from fantasy to a distant engineering challenge. The scientific community reacted with profound skepticism, and rightly so. Extraordinary claims require extraordinary evidence, and the measured thrust was minuscule, sitting right at the edge of what their equipment could detect. The hunt for experimental error began. Could the thrust be from thermal expansion of the device as it heated up? Was it an interaction with the Earth's magnetic field? Perhaps it was the subtle push of air molecules still left in the vacuum chamber, or even an electromagnetic interaction with the test stand itself. Over the next several years, independent teams around the world built their own M drives. Some reported null results, seeing nothing at all. Others, including a group in Germany, confirmed a thrust signal, but they also found something crucial. When they rotated their device, the direction of the thrust rotated with it, suggesting the force was not coming from the drive itself, but from an external interaction, likely with the Earth's magnetic field. The most damning evidence came from a team at the Dresden University of Technology in Germany. They built an ultra-sensitive balance and tested the M drive in a near-perfect vacuum with meticulous magnetic shielding. Their results, published in 2021, showed that when they accounted for all known effects, the anomalous thrust disappeared. The signal, they concluded, was likely caused by the thermal deformation of the test apparatus and subtle forces from the power cables. For many, this was the final nail in the coffin, a clear debunking. Yet, the story does not have a clean ending. Proponents argue the Dresden test used a flawed cavity design that was not optimized, and that the true quantum vacuum explanation for the thrust was not properly tested. The controversy lingers because the dream it represents is so powerful. The M drive stands as a monument to a beautiful, impossible idea, a cautionary tale about the seduction of breakthrough physics, and a testament to the rigorous, often messy process of science itself. It is an anomaly that, for a moment, made us believe we could cheat the universe's most fundamental rules, only to remind us that those rules are remarkably stubborn. The M drive promised a force from nothing, but our cosmic inventory faces an even more fundamental accounting error, one concerning the very stuff of stars and planets and us. We call it the missing baryon problem. Baryons are the particles that make up ordinary matter, the protons and neutrons in every atom. For decades, cosmologists have been able to calculate with great confidence exactly how much of this normal matter should have been created in the Big Bang. They do this by studying the cosmic microwave background, that ancient light which acts as a detailed receipt from the universe's first moments. That receipt says a specific percentage of the cosmos, about 5%, should be baryonic matter. Yet, when astronomers add up everything they can see in the nearby modern universe, all the stars, galaxies, glowing gas clouds, and dust, they come up short, embarrassingly short. We can only find about half of the ordinary matter that our theories insist must be there. So where is the rest of the universe's normal stuff? The leading suspect is not in some hidden dimension, but in the most obvious and hardest to see place imaginable, the vast, empty stretches between galaxies. Our universe is not a random scattering of star cities. It is structured like a colossal spiderweb, with galaxies clustered along dense filaments of dark matter. Theorists predicted that the spaces in this cosmic web should be threaded with faint, diffuse filaments of ordinary matter, gas so hot it glows not in visible light, but in far ultraviolet and soft X-ray wavelengths. They named this elusive component the warm-hot intergalactic medium, or the WIM. Picture steam rising from a network of hot springs across a continent, but on a scale so vast it connects galactic superclusters. This gas is incredibly sparse, maybe just a few atoms per cubic meter, but it fills such an enormous volume that it could easily account for every single missing baryon. The challenge is seeing it. Detecting something that faint is like trying to spot the fine mist from a single spray bottle while floating in the middle of the ocean. Astronomers have had to become cosmic detectives using indirect methods. One clever technique involves looking at the light from brilliant, distant quasars, the luminous cores of ancient galaxies. As that light travels billions of light years to reach us, it passes through these invisible filaments. Atoms in the WIM, like oxygen and hydrogen, absorb specific wavelengths of that light, leaving tiny, telltale dips in the quasar spectrum. It's like analyzing the beam of a distant lighthouse through a giant, diffuse fog. looking for the specific colors the fog has filtered out, piece by piece, using data from space telescopes like Hubble and Newton. Scientists have begun to find these absorption signatures, confirming that the WIM is real and that it contains a significant amount of matter. The hunt is now a race to map it, to weigh it, to see if its total mass finally balances the cosmic books. Solving this mystery is not just about finding lost atoms, it's about validating our entire story of cosmic evolution from the first second to the present day. If the WIM holds the missing half, then our model is complete, and the ordinary universe is simply hiding in plain sight, in the faint, hot breath between the stars. If it doesn't, then we have a far more serious problem, a fundamental flaw in how we count the contents of reality itself. The universe has a built-in speed limit for its most powerful particles, a law written in the fading glow of creation itself. It is called the GZK cutoff, named for the three physicists who predicted it, Greisen, Zatsepin, and Kuzmin. Their idea was elegantly simple. The cosmos is not empty, it is filled with the ancient light of the cosmic microwave background, a sea of low-energy photons left over from the Big Bang. When a proton, a cosmic ray, traveling from a distant galaxy, approaches the very highest energies imaginable, it should begin to interact with this photon sea. The collision is so violent that it blasts the proton apart, creating a shower of lesser particles. This process acts like a cosmic friction, a hard energy sealing that no proton from beyond our local galactic neighborhood should be able to breach. According to the theory, we should never detect an ultra-high-energy cosmic ray from a source more than about 150 million light-years away. Its journey would be cut short by that omnipresent microwave static. For decades, this was a firm prediction, a boundary on the particle map of the universe. Then, our detectors on Earth began catching bullets that should not exist. Experiments like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah are vast networks designed to catch the rare, catastrophic air showers produced when these ultra-high-energy cosmic rays strike our atmosphere. They have recorded multiple events with energies far above the GZK limit. These are not just slightly over the line, they are monsters, particles carrying the kinetic energy of a well-thrown baseball compressed into a single subatomic speck arriving from deep space. The immediate question is, where are they coming from? If the GZK limit holds, then these particles must have originated very close to us, cosmically speaking, within our local supercluster of galaxies. But when astronomers trace their incoming trajectories back into the sky, they do not point to any obvious, powerful nearby sources like active galactic nuclei or colliding galaxies. The skies in those directions are suspiciously quiet. This leaves us with three unsettling possibilities, each profound in its own way. First, perhaps there are incredibly powerful, unknown accelerators lurking in our galactic backyard, cosmic engines we have not yet identified. Second, and more radical, our understanding of particle physics at these insane energies might be incomplete. Maybe protons can interact with the cosmic microwave background in ways we have not predicted. Or perhaps these are not protons at all, but heavier atomic nuclei that behave differently. The third possibility is that our measurements are somehow flawed, that we are misinterpreting the air showers these particles create. Yet, the consistency of the data from multiple, independent observatories makes this last option increasingly hard to believe. The GZK anomaly is a collision between theory and observation at the very frontier of energy. It tells us that the universe might be firing incomprehensibly powerful bullets at us from point-blank range, and we have no idea what the gun looks like or if the bullets themselves are playing by rules we have yet to write down. But even the trajectories of cosmic bullets may be easier to map than the very distances to the galaxies they come from. For over a century, the redshift of light has been our most trusted ruler for measuring the cosmos. As the universe expands, it stretches the light from distant galaxies, shifting it toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding, and according to our standard model, the farther away it is. This relationship should be smooth and continuous. A seamless gradient of recession speeds across the vastness of space. Yet, a small group of astronomers has presented data for decades that suggests something profoundly strange. They claim that the redshifts of galaxies are not random. Instead, they appear to cluster around specific preferred values, as if the universe's expansion is marked in distinct steps like the rungs of a cosmic ladder. This is the claim of redshift quantization. If true, it would be one of the most shocking discoveries in the history of cosmology. It would mean that galaxies are not scattered randomly through an expanding void. Instead, they will be arranged in vast, concentric shells centered on our own Milky Way, with each shell corresponding to a specific redshift step. The implication is staggering and, for many, deeply uncomfortable. It would suggest that our galaxy sits at or near the very center of this shell-like structure, a direct challenge to the cosmological principle which states the universe has no center and looks the same everywhere. Proponents of the idea, like astronomer William Tift, who began publishing on this in the 1970s, point to analyses of galaxy surveys that show curious peaks in the distribution of redshifts. They argue the pattern is too strong to be mere chance, hinting at a universe with a fundamental, rhythmic architecture we do not yet understand. The backlash from the mainstream scientific community has been intense and sustained. Critics argue vehemently that the quantization signal is a statistical mirage. They point to selection biases in how galaxies are chosen for surveys, the complex motions of galaxies within clusters that can muddy the redshift signal, and the fact that different research groups using different datasets often fail to reproduce the exact same quantized steps. The debate is a classic clash between a radical interpretation of data and the conservative standards of a field built on smooth, continuous expansion. Could there be a less earth-shattering explanation? Some have proposed that if the quantization is real, it might not point to a shell-like universe, but to something else entirely, perhaps a previously unknown property of light itself as it travels across cosmic distances, or a cyclic, pulsed nature to the expansion of space. But these ideas remain on the far fringe. For now, redshift quantization stands as the ultimate cosmological heresy. It is an anomaly that, if verified, would force us to tear up our maps of the universe and confront the unnerving possibility that we occupy a truly special place. Yet its persistence in some datasets, despite decades of criticism, means it cannot be entirely ignored. It lingers as a ghost in the numbers, a faint, rhythmic whisper from the data that asks a question we are almost afraid to answer. Does the universe expand in a smooth breath or in a series of distinct, measurable heartbeats? While redshift quantization questions the structure of the cosmos, a perfect geometric wonder spins in our own solar system, a masterpiece of atmospheric engineering. At Saturn's North Pole, a storm of staggering precision has raged for at least 4 decades. It is not a circular hurricane, but a near-perfect hexagon, a 6-sided jet stream wider than 2 Earths placed side by side, with walls of cloud so tall they would dwarf our highest mountains. This is the Saturn hexagon, and it is the most striking geometric weather pattern ever seen. The Voyager probes first glimpsed it in the early 1980s, a strange, angular shadow in the hazy images of Saturn's north. Scientists wondered if it was a temporary fluke, a trick of the light. Then, decades later, the Cassini spacecraft arrived for a long-term study of the ringed planet. As Saturn's northern hemisphere emerged from its long winter into sunlight, Cassini's cameras revealed the hexagon was not only still there, but it was stunningly vivid and stable, a permanent fixture painted in swirling bands of yellow and gold. This persistence is the core of the mystery. On Earth, weather systems are chaotic and transient, lasting days or weeks. Jupiter's Great Red Spot is a long-lived storm, but it is an oval, a shape fluids naturally tend to form. A hexagon is different. It is a shape of structure and stability, of boundaries that have held their form against the turbulent, raging winds of a gas giant for generations. How does nature draft such perfect geometry on a planetary scale? The leading theory comes from the world of laboratory fluid dynamics. Researchers have created similar polygonal shapes, including hexagons, by placing a cylinder of fluid on a rotating turntable. When the rotation speed of the central cylinder differs from the rotation of the outer container, the shear between these layers can organize the flowing liquid into stable geometric patterns. This suggests the hexagon is a standing wave, a pattern etched into Saturn's fast-moving jet stream by some deeper interaction. Perhaps it is anchored by a giant vortex at the pole, or shaped by differences in wind speed at various latitudes. The Cassini data showed the hexagon is a towering wall of air, a jet stream where winds scream at over 200 miles per hour, with a massive, rotating storm possibly sitting at its center like the axle of a wheel. Yet, the exact recipe that creates and, more importantly, sustains this six-sided pattern for so long remains elusive. The laboratory models are compelling, but they are simplifications of a planet-sized system with unknown depths, compositions, and energy flows. The Saturn hexagon is a breathtaking demonstration that the universe has a hidden flair for art. It is a natural tattoo on the face of a giant, a structure so precise it looks manufactured, yet it is a purely natural phenomenon. It asks us a beautiful question: what other sublime and orderly secrets might be hiding in the swirling atmospheres of distant worlds, waiting for a patient observer to bring them into the light? Saturn's geometric storm is a masterpiece of natural physics, but it was a visitor from another star that delivered a mystery of pure motion. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint, fast-moving dot of light. Its trajectory was unlike anything seen before, a hyperbolic path so extreme it could only mean one thing: this object was not from our solar system. It was the first confirmed interstellar visitor, and astronomers named it Oumuamua, Hawaiian for scout from the distant past. This dark, reddish, tumbling rock was already a historic discovery, but as telescopes tracked its departure, they captured something that defied simple explanation. As Oumuamua sped away from the Sun, it did not follow a path dictated by gravity alone. Its velocity changed slightly, accelerating in a way that could not be accounted for by the gravitational pull of the Sun or planets. This was a non-gravitational acceleration, a tiny push coming from the object itself. For comets, this is a common sight caused by outgassing. As a comet's icy nucleus heats up near the Sun, it vents jets of gas and dust that act like natural thrusters, subtly altering its orbit. The problem was, Oumuamua showed no visible signs of outgassing. No surrounding coma of gas, no dusty tail, nothing in the data from our most powerful instruments. It looked and behaved like a silent, inert asteroid, yet it was accelerating like a comet. This contradiction became the central puzzle. The leading scientific explanation is that Oumuamua was indeed a comet, but an exotic one. Perhaps its outgassing came from very specific jets located in cracks or vents on its surface, releasing a pure, invisible gas like hydrogen or carbon monoxide without producing the reflective dust that would create a visible tail. If its ices were largely depleted or its surface was covered in a thick, insulating crust, the venting could have been faint and highly directional, providing just enough thrust for the observed acceleration without the usual cometary display. This remains the most parsimonious answer, fitting within known physics, even if it requires a somewhat unusual object. Yet, the absence of a clear signal left room for a more sensational hypothesis. Could the acceleration have been caused by radiation pressure from the Sun? For that to work, Oumuamua would need to be extraordinarily thin and light, like a sheet of material only a fraction of a millimeter thick. This led a prominent astronomer to cautiously suggest it might resemble an artificial light sail, a piece of technology designed to be propelled by starlight. While this captured the public imagination, the scientific community largely finds it an unnecessary leap. No artificial radio signals were detected from it, and nature is quite capable of creating thin, flat objects through processes like the tidal disruption of a larger body. The true frustration, and the reason this anomaly remains so potent, is that Oumuamua is now gone, receding into the interstellar dark far beyond the reach of our telescopes. We had only a few weeks of fleeting observations of a faint, enigmatic speck. We may never know its true composition or the exact source of its mysterious push. Oumuamua stands as a ghost at the edge of our data, a silent scout that passed through our neighborhood, gave us a tantalizing, contradictory clue, and then vanished forever, leaving behind a simple, haunting question: what other strange travelers are sailing the void between the stars, and what secrets do they carry about the formation of other solar systems? While Oumuamua was a fleeting mystery from beyond our solar system, our own planet's ancient history holds a paradox written in stone and sunlight. Billions of years ago, our sun was not the steady, mature star we know today. In its youthful state, it burned about 30% fainter, a cooler, dimmer version of itself. According to straightforward physics and climate models, that weaker sun should not have been able to keep Earth's surface above freezing. The entire planet, for its first 2 billion years, should have been a global snowball, a frozen wasteland locked in permanent ice. Yet the geological record screams the opposite. The oldest rocks on Earth, some dating back nearly 4 billion years, show clear, undeniable evidence of liquid water. There are sedimentary layers that only form in flowing rivers and deep oceans, and mineral deposits like pillow basalts that are created when lava erupts underwater. Some evidence even suggests the early Earth was warmer than it is today, a veritable tropical paradise under a faint young sun. This glaring contradiction is the faint young sun paradox, and it strikes at the heart of our understanding of planetary climate and the origins of life itself. How did Earth stay warm enough for oceans to flow, and possibly for life to first stir under such a dim stellar lamp? The leading solution points to the planet's own atmosphere acting as a colossal thermal blanket. Today, greenhouse gases like carbon dioxide and methane trap heat and keep our world habitable. On the early Earth, the atmosphere was likely far denser with these gases, creating a supercharged greenhouse effect that compensated for the lack of solar warmth. Volcanic activity was more intense, constantly pumping carbon dioxide into the air, and there were likely no land plants or weathering processes to efficiently remove it. Another factor could have been the planet's reflectivity, or albedo. With fewer continents and a darker, rockier surface not yet covered by bright ice or forests, the young Earth may have absorbed more of the sun's precious heat rather than reflecting it back into space. There is even a more speculative idea involving ammonia, a potent greenhouse gas that could have been present in the atmosphere, though it is easily broken down by sunlight. Solving this paradox is not just an academic exercise for climate scientists, it is a cornerstone of astrobiology. If we cannot explain how our own planet remained habitable under challenging conditions, how can we accurately assess the potential for life on distant exoplanets orbiting other faint young stars? The faint young sun paradox forces us to appreciate the delicate, dynamic interplay between a planet and its star, a dance of gases, geology, and light that somehow, against the odds, kept our world cradled in liquid water and set the stage for everything that was to come. The faint young sun paradox reminds us that even our own planet's climate history is filled with unanswered questions, but a far more pressing crisis is unfolding across the entire cosmos, one that threatens to crack the very foundation of modern cosmology. It is called the Hubble tension, and it is a disagreement over the single most important number in the universe, the rate at which everything is expanding. For a century, we have known the cosmos is growing, with galaxies racing away from each other like dots on an inflating balloon. The speed of that expansion is the Hubble constant, and pinning down its exact value is the master key to understanding the universe's age, its size, and its ultimate fate. For decades, astronomers have pursued two brilliant, independent paths to measure this number, and both methods are exquisitely precise. The problem is, they give two different answers, and the gap between them is only growing wider. One path looks back to the universe's infancy, to the cosmic microwave background. By mapping the subtle wrinkles in that ancient light with satellites like Planck, cosmologists can work backwards through our best model of cosmic evolution, the lambda-cold dark matter model. This model accounts for all the known ingredients: dark energy, dark matter, and ordinary matter, and it spits out a predicted expansion rate for today. That value is about 67 kilometers per second per megaparsec. This means that for every megaparsec, a distance of about 3.3 million light-years, a galaxy appears to be moving away 67 kilometers per second faster. This is the early universe's prediction for how fast space should be stretching now. The other path measures the universe directly in the present day, our local neighborhood. Astronomers use celestial landmarks called standard candles, stars, and supernova whose intrinsic brightness we know. By measuring how bright they appear from Earth, we can calculate their exact distance. Then, by measuring how much their light is redshifted, we know how fast they are receding. Combine distance and velocity across many galaxies, and you get a present-day measurement of the Hubble constant. Teams using the Hubble Space Telescope, along with ground-based observatories, have refined this local measurement to an astonishing precision. Their answer is about 73 kilometers per second per megaparsec. That is a significant and stubborn difference. 6 kilometers per second might not sound like much, but the uncertainty bars on these measurements, the tiny ranges of possible error, no longer overlap. Statistically, this is not a fluke or a minor calibration issue. This is a 5-alarm fire in cosmology. The early universe method and the late universe method are both incredibly robust, yet they disagree by about 9%. It is as if you used two perfectly engineered clocks to time a race, and one consistently said the runner finished in 9.8 seconds, while the other insisted it was 10.7 seconds. Both clocks are working perfectly, but they cannot both be right. This tension implies something profound is missing from our standard cosmological model. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant but has changed strength over cosmic history. Maybe dark matter interacts with itself or with ordinary matter in ways we never anticipated. There could even be a new, unknown type of neutrino or another relativistic particle zipping through the early cosmos, altering its expansion history just enough to throw off the prediction. Some have even suggested more radical ideas, like a flaw in our understanding of gravity itself on the largest scales, or that our local region of the universe is somehow atypical, a giant void that is skewing our local measurements. Every proposed solution faces intense scrutiny, and so far, none have gained universal acceptance without creating new problems elsewhere. The Hubble tension is not just a technical disagreement, it is a direct challenge to our story of the cosmos from the first second to the present day. It tells us that one of our most cherished maps of reality, assembled over a century of observation, has a fundamental crack running right through its center. The race is on to find the source of the crack, and the winner will not just settle a scientific debate, they will redefine our understanding of the universe's very heartbeat. The Hubble tension reveals a crack in our cosmic model, but on the ground we catch bullets that point to empty rooms. The most powerful particles in the universe, ultra-high-energy cosmic rays, rain down on Earth in a near-uniform drizzle from all directions. Their immense charge makes them puppets of galactic magnetic fields, their paths twisted and scrambled over millions of light years until all sense of their origin is lost. Or so we thought, When scientists at the Pierre Auger Observatory in Argentina mapped the arrival directions of the very highest energy events, those above a certain staggering threshold, a faint pattern emerged against the random noise. Not a single clear source, but intriguing, localized excesses, hotspots in the cosmic ray sky. These are places where an unexpected number of these atomic bullets seem to be coming from. The mystery deepens when you look at what, or rather what isn't, in those patches of sky. You would expect the universe's most powerful particle accelerators to be its most spectacularly violent objects, things like active galactic nuclei, where supermassive black holes shred matter and blast out jets of energy, or colossal collisions between entire galaxies. Yet when astronomers trace a line back from these hotspots, they often find nothing. No brilliant quasar, no raging starburst galaxy, just a relatively quiet, unremarkable stretch of the cosmic void. It is like finding a cluster of bullet holes on a wall and discovering the gunshots came from an empty field. So what is firing these particles at us? The leading idea is that the sources are there but hidden. Perhaps they are intermittent, only blasting out these ultra-high-energy beams in short, brilliant bursts that have since gone quiet, leaving only their high-velocity shrapnel to reach us millions of years later. Or maybe the sources are just far enough away that their light is too faint for our current telescopes to see, but their particles traveling nearly at light speed still make the journey. Another possibility is that our understanding of how these particles propagate through the intergalactic medium is flawed. Could there be pockets of space where magnetic fields are weaker, allowing straighter paths that point more truly back to a distant known source? Or are we seeing the collective fingerprint of many smaller, closer sources, like a type of neutron star we haven't yet recognized as capable of such acceleration? Each hotspot is a cosmic crime scene with no visible weapon. Solving it requires a new kind of detective work, combining particle physics with astronomy in a field called multi-messenger astrophysics. The hope is that one of these ultra-high-energy cosmic rays will arrive at the same time as a different cosmic messenger, like a burst of neutrinos or a ripple in space-time from a gravitational wave from the same patch of sky. That coincidence would be a smoking gun, finally identifying the engine behind these mysterious accelerators. For now, these hotspots remain tantalizing and frustrating targets, bright blips on a particle map that lead our eyes to darkness, hinting that the universe's most powerful cannons might be firing in the dark, or that we simply do not yet know what we are looking for. But if cosmic hotspots point to empty rooms, a theoretical ghost haunts the very concept of empty space itself, a ghost predicted to appear for anyone who pushes the accelerator hard enough. According to quantum field theory, the vacuum of space is not truly empty. It is a seething, bubbling sea of virtual particles, constantly flickering in and out of existence in pairs. For an observer floating peacefully through this vacuum, these quantum fluctuations remain perfectly balanced and invisible. But for an observer undergoing intense, constant acceleration, something extraordinary should happen. The theory predicts that this observer would not see a calm vacuum. Instead, they would perceive themselves as being immersed in a warm bath of real, detectable radiation. This is the Unruh effect, a mind-bending consequence of quantum physics and relativity, named after physicist William Unruh, who described it in the 1970s. In essence, acceleration itself should heat up the void, making particles appear from what a stationary observer sees as nothing. It is a direct cousin to Hawking radiation, the process by which black holes are predicted to slowly evaporate. In both cases, the intense gravitational field near a black hole, or the intense acceleration of an observer, disrupts the quantum vacuum, turning virtual particles into real energy you could, in theory, measure with a thermometer. The profound implication is that the very concepts of temperature and particles are not absolute, but depend entirely on your state of motion through the universe. An astronaut in a gently coasting ship sees a cold, dark emptiness outside the window. An astronaut in a ship undergoing savage, sustained acceleration would look at that same patch of space and see it glowing with heat. Yet, for all its theoretical elegance, the Unruh effect remains just that, a theory. It has never been observed. The reason is brutally simple. The accelerations required to produce a detectable temperature are almost unimaginably huge. To see the vacuum glow at a temperature of just 1 degree above absolute zero, you would need to accelerate at 1 quintillion times the force of Earth's gravity. That is a 1 with 18 zeros after it. No human-made object, no particle in our most powerful accelerators can withstand or achieve such forces for the necessary length of time. It is an effect reserved for the edges of theoretical possibility, near the event horizons of black holes or in the cataclysmic moments of the universe's birth. This creates a fascinating and profound anomaly, a glaring gap between a robust, widely accepted prediction of our most successful physical theories and our complete inability to test it empirically. The Unruh effect sits at the crossroads of quantum mechanics and general relativity, a realm where our understanding is mathematically beautiful but experimentally untouchable. It forces us to ask a humbling question: how many of the universe's deepest secrets are written in a language of extremes so great that we may never build a laboratory capable of reading them aloud? The Unruh effect remains a ghost in the equations, but our own galaxy holds a fossil of violence written across the sky in radio whispers. If you could see the universe through eyes that perceive radio waves, the serene band of the Milky Way would be slashed by 2 colossal, faint hoops. These are the galactic radio loops, immense arc-like structures that rise tens of thousands of light-years above and below the galactic plane, curving around the center like the ribs of a cosmic umbrella. Discovered in the early days of radio astronomy, they have been a quiet, persistent mystery for decades, a signature of some ancient cataclysm at the heart of our home. Their light is not the warm glow of stars, but the cool, precise signature of synchrotron radiation. This is the light emitted by electrons spiraling at nearly the speed of light along powerful magnetic field lines. The loops are, in essence, the ghostly tracings of invisible magnetic architecture painted by high-energy particles. Their sheer scale is humbling. Loop 1, the most prominent, stretches over 600 degrees across our sky, a distance of nearly 30,000 light-years from end to end. This is not a small, local feature. It is a structure on a galactic scale, a remnant of an energy release so powerful it could only come from the most titanic events the Milky Way can produce. So what carved these faint, perfect arcs into the fabric of our galaxy? The leading theory points to a frenzy of creation and death. The loops may be the fossilized shockwaves from a period of intense starburst activity near the galactic center, a time when thousands of stars were born in rapid succession. The most massive of these stars would have lived fast and died young, exploding as supernova in a cascading chain reaction. The collective blast waves from these stellar deaths could have inflated gigantic bubbles in the interstellar medium, pushing out magnetic fields and accelerating particles to relativistic speeds, creating the radio-bright shells we see today. Another possibility is that they are tidal debris, the shredded remains of a small satellite galaxy that ventured too close to the Milky Way's core and was torn apart by gravitational forces, its material stretched into these vast, luminous streamers. Or perhaps they are a purely magnetic phenomenon, a glimpse of the galaxy's underlying dynamo, where kinks and instabilities in the global magnetic field somehow focused and trapped energetic particles into these perfect looping shapes. The truth is, we do not yet know. These loops are a palimpsest, a faded text overwritten on the sky, telling a story of the Milky Way's violent adolescence that we are still learning to read. They remind us that our galaxy is not a static painting, but a dynamic, evolving entity with a history written in eruptions and echoes. Every new, sensitive radio survey that maps their faint light is an attempt to listen to that history, to understand the silent, colossal explosions that once rocked our galactic home and left their indelible mark on the void. The galactic radio loops are echoes of ancient stellar violence, but far closer to home. A different kind of energy dances with a life of its own. For centuries, sailors, pilots, and ordinary people have reported seeing spheres of light drift calmly through the air during thunderstorms. These are not the jagged bolts of common lightning, but self-contained orbs, often the size of a grapefruit or a beach ball, glowing with an eerie, sustained light. They float along walls, hover over furniture, sometimes even seem to pass through solid glass or metal before vanishing with a silent pop or a violent bang. This is ball lightning, one of the most persistent and bizarre atmospheric anomalies in human history. A phenomenon so strange it feels like a piece of a star has fallen to Earth. While it is not a cosmic glitch in the fabric of space-time, its very existence challenges our understanding of physics, presenting a mystery of stability and behavior that science has struggled to cage in a lab. The accounts are too numerous and too consistent to dismiss. A famous early scientific report comes from the 18th century, when physicist Georg Richman was killed in St. Petersburg while attempting to study atmospheric electricity, with witnesses describing a blue fireball leaping from his apparatus. These glowing spheres defy the basic nature of a plasma, which is a hot, chaotic soup of charged particles that should dissipate in milliseconds. Yet ball lightning can last for many seconds, even minutes, maintaining a coherent, often spherical shape as it drifts against the wind, as if it has its own internal logic. For a long time, the scientific community treated these reports with deep skepticism, relegating them to the realm of optical illusions or overactive imaginations. That changed as credible witnesses multiplied, including airline pilots and trained military observers. The quest then became not to prove it exists, but to explain how it can possibly exist. The breakthrough towards a physical explanation came from an unexpected direction: the Hubble soil. In 2014, a team of scientists in China accidentally recorded high-speed video of ball lightning forming naturally after a cloud-to-ground strike. Spectroscopic analysis of the light revealed the unmistakable signature of silicon, iron, and calcium, elements abundant in soil. This supported a compelling theory that when lightning strikes the ground, it can instantly vaporize silicate materials in the soil. The vapor condenses into a fine, glowing network of nanoparticles that are chemically active, slowly burning in the air as they interact with oxygen. This creates a floating, persistent ball of energized matter, a kind of terrestrial star in miniature. Other theories propose that the phenomenon is a microwave cavity, where the electromagnetic energy from a lightning strike becomes trapped in a standing wave of plasma, essentially creating a bubble of confined light. Or perhaps it is a form of atmospheric maser, a naturally occurring microwave amplification that energizes the air itself into a glowing state. The fact that we can now, very rarely, create short-lived ball-like plasmas in laboratories using powerful microwave ovens or electrical discharges gives credence to these ideas, but the full picture remains elusive. The true anomaly of ball lightning is its eerie combination of longevity, motion, and apparent intelligence. Why does it often seem to move with purpose? How does it maintain its energy without a continuous power source? Solving this terrestrial riddle could do more than explain a weather oddity. It could open doors to new understandings of plasma physics and exotic states of matter, showing us that even within our own atmosphere, pockets of reality can behave by rules we have only begun to glimpse. Ball lightning is a fleeting mystery in our own sky, but the greatest discrepancy in all of science is woven into the fabric of empty space itself. This is the vacuum catastrophe, a failure of prediction so spectacular it is often called the worst in the history of physics. To understand it, we must look at nothing, the pure, perfect vacuum. According to quantum field theory, this emptiness is not empty at all. It is a seething, turbulent foam where virtual particle pairs constantly blink in and out of existence. Every cubic centimeter of this quantum vacuum should be crackling with an immense intrinsic energy. When physicists calculate the density of this vacuum energy, the number they get is staggering, a 1 followed by 120 zeros. That is a 10 raised to the power of 120. Now compare that to the energy we actually observe in the cosmos. For decades, astronomers have known the expansion of the universe is accelerating, driven by something we call dark energy. We can measure the strength of this dark energy by observing distant supernova and the large-scale structure of the cosmos. The observed density of dark energy, the energy actually causing the cosmic acceleration, is a very small, finite number. When you place the theoretical prediction from quantum mechanics next to the observed value from cosmology, they should match. They are, in principle, describing the same thing, the energy of empty space. But they do not match, not even close. The theoretical value is larger than the observed value by a factor of 10 to the 120th power. That is not a small error. It is not a factor of 2 or 10 or even a million. It is a number so incomprehensibly large that writing it out would fill volumes. If the theoretical prediction were correct, the vacuum energy would be so powerful it would have ripped every atom in the universe apart in an instant after the Big Bang. Reality clearly did not get the memo. This 120 order of magnitude gap is the vacuum catastrophe. It represents a fundamental disconnect between our two most successful theories, quantum mechanics, which governs the very small, and general relativity, which governs the very large. Quantum field theory gives us an answer that is catastrophically wrong when applied to the cosmos. This tells us something profound. Our understanding of the vacuum is broken. Perhaps the quantum fluctuations somehow cancel each other out with near-perfect precision, leaving only the tiny residue we see as dark energy. But why would they cancel to one part in 10 to the 120? That level of fine-tuning seems absurd, like balancing a pencil on its tip for billions of years. Alternatively, it may be that the concept of vacuum energy in quantum field theory simply does not apply to gravity the way we think it does. Reconciling these two numbers, bridging this unimaginable gap, is arguably the single most important goal for any theory of quantum gravity, for any attempt to unify the laws of the cosmos. The vacuum catastrophe is not just a math problem, it is a screaming alert that our map of reality is missing its most foundational piece, the true nature of nothing itself. This ultimate failure of prediction, the vacuum catastrophe, exposes a chasm between our theories of the small and the large. But perhaps the most famous and elegant demonstration of that conflict occurs at the edge of a black hole, in a paradox that threatens the very logic of reality. Stephen Hawking's greatest insight was that black holes are not truly black. Through quantum effects at their event horizons, they should slowly leak radiation and evaporate over eons. This Hawking radiation is a gentle glow that carries away the black hole's mass and energy until, theoretically, it vanishes completely, and here lies the catastrophe. According to the pristine rules of quantum mechanics, information can never be destroyed. If you burn a book, the information in its pages is not truly gone. In principle, a being with godlike powers could collect every photon, every wisp of smoke and ash, and reconstruct the entire book from the chaotic aftermath. This principle is called unitarity, and it is the bedrock of quantum theory. It says the universe keeps perfect, unerasable records, but Hawking radiation creates a terrifying exception. Imagine a book or a star or an entire civilization falling into a black hole. All the information about what fell in, the arrangement of its atoms, its history, its story, is seemingly trapped behind the event horizon. Then, over trillions of years, the black hole evaporates via Hawking radiation. The radiation that escapes, according to Hawking's original calculation, is purely thermal, random noise. It carries no fingerprint, no hidden code, no memory of what created the black hole in the first place. When the black hole is gone, all that remains is this formless heat. The information is lost forever. This is the black hole information paradox. It forces a brutal choice. Either quantum mechanics is wrong and information can be destroyed, unraveling the foundation of modern physics, or general relativity is wrong, and our picture of black holes and their event horizons is fundamentally flawed. For decades, this was the standoff. Then, possible solutions emerged, each more mind-bending than the last. One revolutionary idea is holography. It proposes that all the information about what fell into the black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface. The three-dimensional interior is an illusion, a projection from the data on the boundary. When the black hole evaporates, that information is slowly and chaotically released in the Hawking radiation, scrambled beyond easy recognition but never truly erased. Another, more violent solution is the firewall hypothesis. It suggests that the event horizon is not a smooth, empty space as Einstein predicted, but a searing wall of high-energy particles. Anything crossing it would be instantly incinerated. This firewall would prevent information from ever falling into the black hole in the first place, preserving it in the violent interaction at the boundary, but at the cost of violating Einstein's principle that crossing the horizon should be uneventful. The debate rages on with other ideas like black hole remnants or subtle quantum connections called entanglement playing key roles. This is not an abstract academic debate. The black hole information paradox is a direct probe into how space, time, and information are woven together. It asks what truly happens to reality when it is stretched to its absolute limit. Solving it would not just tell us about black holes, it would reveal the hidden grammar that writes the story of the universe itself. A grammar where not a single letter, not a single bit of cosmic data is ever allowed to be forgotten. The black hole information paradox asks if reality keeps perfect records, but a far simpler experiment performed on a tabletop has already shattered our most basic intuition about how the universe connects. This is the EPR paradox, and the phenomenon it describes, quantum entanglement, is perhaps the most well-tested and profoundly strange anomaly in all of physics. It is the foundational glitch that makes the quantum world so bizarre, and in many ways it underpins the possibility of all the other mysteries we have explored. The story begins not with complex machinery but with a thought experiment. In 1935, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper aiming to show that quantum mechanics, with its probabilistic nature, must be incomplete. They envisioned a pair of particles born from a single event becoming entangled. According to quantum theory, these particles would share a single, unified quantum state. You could separate them by any distance, light years apart, and measuring one would instantly determine the state of the other. Einstein called this spooky action at a distance. He argued this was impossible, as it seemed to require information traveling faster than light, violating relativity. He believed there must be hidden variables, unseen properties set at the moment of entanglement that predetermined the outcomes, preserving a local, sensible reality. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a brilliant mathematical test. Bell's theorem showed that if hidden local variables were real, then entangled particles would obey certain statistical limits known as Bell inequalities. If quantum mechanics was correct, these limits would be violated. It was no longer a matter of philosophy, it was an experiment waiting to happen. The first decisive tests came in the 1980s by Alain Aspect and his team in France. They created pairs of entangled photons and measured their properties at detectors placed far apart. The results were unequivocal. the Bell inequalities were violated spectacularly. The particles were correlated in ways that no local hidden variable theory could ever explain. Spooky action was real. This means if you measure the spin of one entangled electron here on Earth and find it is up, its partner, even if it is on the other side of the galaxy, instantly becomes down. There is no signal, no communication, no exchange of force. The connection is immediate and seems to transcend space. It is as if the universe does not see them as two separate objects, but as a single entity, a unified whole that exists in multiple places at once until you force it to choose. This is quantum nonlocality. It challenges the classical notion of locality, the idea that objects are only influenced by their immediate surroundings, and it stretches our understanding of causality to the breaking point. How can something here affect something there without any time for a signal to travel? The prevailing interpretation is not that information travels faster than light, which relativity forbids, but that the entangled particles exist in a shared reality where concepts like here and there are not fundamental until a measurement is made. Space itself may be a secondary property emerging from a deeper, interconnected quantum network. This anomaly is not just a laboratory curiosity. It is the operating principle behind emerging technologies like quantum computing and quantum cryptography. It is the strange bedrock upon which our most accurate theories of matter are built, and it whispers that the separateness we experience, the vast, cold distances between stars, may be an illusion. At its most fundamental level, the universe may be a single, entangled system, where every particle remembers its connection to every other, and the fabric of space-time is merely the stage upon which this deeper, instantaneous connection plays out. It is the ultimate mystery, the silent hum of a universe that is far more connected and far stranger than we ever dreamed. These 25 cosmic glitches are not failures of our science, but its most vital successes. They are the places where the universe itself has whispered a secret or shouted a contradiction, forcing us to listen more closely. From the gentle, phantom tug on a pair of aging spacecraft to the universe shattering tension in its very expansion rate, each anomaly is a signpost at the edge of our understanding. They prove that our maps of reality are not finished, that blank spaces remain where the words, "Here be dragons," are not a warning but an invitation. Every unexplained drift, every missing particle, every impossible geometric storm is a frontier. It is a crack in the facade of known physics where new light might shine through, potentially illuminating a revolutionary truth about dark matter, quantum gravity, or the nature of time itself. This journey through the glitches is a tour of human curiosity in action, a testament to our refusal to accept that the story is fully written. So stay curious. The next great discovery, the one that rewrites the textbooks, could be hiding in the precise measurement of a distant quasar's light, in the next inexplicable blip from a deep space probe, or in the quiet contemplation of a paradox born at a black hole's edge. The universe is still talking. We just have to learn how to hear the rest of the conversation. Which of these 25 mysteries captured your imagination the most? Let us know in the comments below, and if you want to join us for more deep dives into the fabric of space and time, be sure to subscribe.